Good afternoon, welcome to Compass on this Wednesday afternoon. Our speaker today is our retired colleague John van Leer, who retired just a few weeks ago after being here at the Rosenstiel School for more than 50 years. That's a goal for all of us to beat that. And his biography is interesting. He grew up in Maryland. He got a bachelor's degree in mechanical engineering at the Case Institute of Technology in Ohio in 1962. Then he spent 3.5 years at the MIT Instrumentation Lab and worked on some systems for intercontinental ballistic missiles. Then he went to the Woods Hole Oceanographic Institution, worked with Henry Stommel in physical oceanography, and got his doctorate degree in 1971. And in the same year, he came here to Miami, to Rasmus. I don't know if it was already, probably not called Rasmus at the time, but
pre-Rasmus.
So
Institute for Marine
not
Science.
Rasmus anymore, and you came here before it was called Rasmus. So that's really interesting. And he started the division of physical oceanography at the time. Then at some point that became the meteorology and physical oceanography. Then a few years ago it became ocean sciences. He's an expert for ocean instrumentation and the impacts of global warming, especially here in coastal Florida. He's also interested in Arctic drivers of these climate changes. He developed a significant instrument called the cycle sonde, which was the first moored automatic ocean profiler system with real-time telemetry for successive generations. It was used in many experiments. He has participated in dozens of research cruises for 4.5 years on the ship altogether, on different ships. About a third of that time as chief scientist in all kinds of oceans you can imagine. I will not read the whole list. He has 32 peer-reviewed articles and book chapters, numerous technological articles. Until his retirement, he still taught undergraduate courses here on the main campus. And in addition to those official professional things, he has always been a climate activist, at least as long as I have known you. Actively involved in international organizations who act to mitigate global warming. And so now he is retired, but still energized and still interested in all these things. And he suggested to give another seminar. His last seminar, actually about 2 years ago, was one of the most watched recordings that we have on our YouTube channel. And let's see if we can repeat that success today. And the topic will be this concept for a net zero carbon research vessel, a very up-to-date topic. So please.
Well, thank you, Roland. Yeah, it's been a little while since I've given one of these, and it just so happens today is National Energy Efficiency Day. So I didn't realize that when this was scheduled, but fits right into the picture. So a lot of people are interested in reducing carbon emissions and other greenhouse gas emissions and promoting sequestration and doing the things that we might do to slow down climate change, or if we're really good, maybe even reverse it in the long term. So the question is, a lot of people study coral reefs and sea level rise and a number of other items that directly relate to climate change. And so the question is, are we going to be serious as scientists and do something about it as well as talk about it? So it's a wonderful thing to understand. I'm not impugning research, that's absolutely essential, but it isn't sufficient. We actually have to take actions in order to make a difference. So this is a reprise of the summary, and basically we as seagoing oceanographers should be setting an example of good behavior in terms of reducing our emissions. If we study it, if we care about it, we should be actually doing something about it. And so we are major contributors to climate change research. The ocean certainly plays as an important part as the atmosphere does, and it particularly interacts with the ice in the Arctic. Both glacial ice and pack ice are affected by what's happened in the ocean, the rate of heat absorption. And it turns out that it's easier to remove heat from the ocean than it is to add it. And so that is something that gives me hope that if we got serious about reducing global warming, we could do something about it. And there's been some serious developments since the passage of the IRA, the Inflation Reduction Act. Like all legislation, it's sausage making, so some of the sausage is good. Some of the sausage I would just assume didn't exist, but on balance, it is about 3/4 of what we need to get the change we need to reduce emissions, to slow down and possibly begin to reverse global warming. We need to do more. We're not doing enough, but it's a whole lot better than nothing. So I've been, as Roland said, involved with various climate groups. I worked with Union of Concerned Scientists during Obama's first term, trying to get the Waxman-Markey bill passed, essentially a cap and trade means of controlling global warming. We came within 2 votes in the Senate. We passed the House. Does that sound familiar? So I'm not easily discouraged. So I kept going at it, and I worked with almost every organization that has worked on climate mitigation or climate change reduction or even reversal. And the one organization that seems to be the most effective of them, and I've worked more with them than anybody else, is Citizens Climate Lobby. And what this diagram shows are 4 different emissions scenarios, and a whole bunch of modeling results, model runs that are color-coded depending on which scenario it is. And so you can see mean scenarios. There's a 5th one that has to do with trying to keep global warming to 1.5 degrees C, which is not graphed here, but it's the one we really need to concentrate on. And Citizen Climate Lobby puts a price on carbon that reduces emissions and possibly takes things down below 0. That's where we really need to get. Because I live in a wonderful seaside community, and this morning as I was driving out, the street was filling with salt water, so I left earlier than I would have chosen to leave otherwise. So I am painfully aware of the impact of what we do. I see it all the time. Gulf Stream slows down when we have a big hurricane passing off of the coast in the Carolinas, and so we get sea level rise. The sea level in the Bahamas is about 3 feet higher than it is here on the coast of Florida, and that difference is sustained by the fact there's a Gulf Stream running up between hither and yon, and so the Earth's rotation wants to turn the water into the Bahamas and to the right in the northern hemisphere, and that's offset by a pressure gradient which has to do with the sloping of the seawater downward towards Miami. So if you shut off the Gulf Stream tomorrow, by tomorrow night we'd have 3 feet more sea level in Miami. So that's another little component to it. So we've got to be serious about this business. And so CCL puts forward a plan called carbon fee and dividend, where we put a price on carbon, but we refund it to everybody in the United States in equal shares. And since everybody gets the same amount, whether you're Donald Trump or whether you're the guy, homeless guy on the street in Miami, it's obviously going to help the guys at the bottom more. Donald won't notice an extra whatever it is per year. So for a family of 4, it gets to be like $4,500. So that's enough you can actually begin to do something after a decade. So anyway, I made a little song up about that. It's carbon pricing hits the spot with refunds. The tax is not save the planet and prosper too. Carbon pricing is the thing to do. So that summarizes what we're trying to do with Citizens Climate Lobby. So we're talking about low carbon or zero carbon research vessels. This one was built in Switzerland, and it happens to be the first solar powered vessel to cross over the Atlantic. It doesn't have a sail on it. It's entirely propelled by propeller, and the propeller gets turned by an electric motor that generates, that uses power from the solar array. So traveling on Sun 21 is like being on your front porch. There's a nice sunshade over you, and so you're traveling in the shade, and you're traveling very quietly. There's no roaring diesel engine anywhere. Paradoxically, in my 4.5 years at sea, I have breathed so much diesel smoke, I can't even begin to tell you, I hate that stuff. That's the thing I like least about doing oceanography as it has been done. So, truth in advertising, one of the sub rosa plots is to get away from doing that kind of stuff to ourselves. I mean, you're working in this beautiful, pristine environment, some of the cleanest air on the planet, and you've got the head of the vessel into the wind, and that diesel smoke is roiling down onto the working deck, and you're breathing so much of that stuff you can hardly breathe. I grew up in Washington traveling on streetcars that were electrically propelled, and a group of corporations put the streetcars out of business in the United States and destroyed $2 trillion worth of infrastructure, and told us that the diesel belching buses we were getting to replace our streetcars were progress. Yay. I didn't buy it then, I don't buy it now. So we should be taking part in the great transition as oceanographers. So this one has a 10.5 kilowatt array on the top of it, divided in two. So it has two completely redundant electric systems, a starboard and a port one. And so we should be looking at this as an example. This is not a very rugged vessel. This was a derivative of boats that were used in an exposition in Switzerland to move 4 million people over a couple of years around on the lakes in Switzerland. And they don't like burning fossil fuel and leaking oil on their water supplies, the lakes. There are laws about that in Switzerland, imagine that. So anyway, we should be taking part in the great transition, and the interesting part of it is that it is getting easier and easier and easier to do, because corporations like Tesla and Norwegian and Swiss ship developments since August '94, when I had an active ship bid to build the vessel I will show you today, should accelerate and be comparable. When I first used solar panels to run the telemetry on the cyclotron moorings that Roland described briefly, they cost $74 to generate a watt of electricity. I had a 4-watt transmitter on the buoy, and I had a gel cell battery about that big, everything hyper efficient, and so I could run for about a week without any sunlight. And with those, and because it was such a small amount of power, I could afford it. Now it's like 15 cents a watt. $74 in 1974 to 15 cents a watt today. Holy moly, where do you ever see energy get cheaper and cheaper and cheaper and cheaper and cheaper? You know, you don't have to burn things, you don't get rid of things, you don't make smoke. It's like magic. And so here's a vessel that was designed to demonstrate the magic. And so one of the questions that always comes up is, what's the difference in cost? So if you figure out what is the energy content of a gallon of diesel or gasoline, in round figures, is 10 kilowatt hours of energy per gallon of liquid fuel. So if you want to know the cost for the electric gallon, essentially it comes down to 10 kilowatt hours times the price of electricity. Last time I checked, it was $0.107 per kilowatt hour. And so that's $1.07 for an electric gallon today. So the Walton Smith uses diesel fuel. I don't know whether it's $7, $5, $8, I don't know what it is, but it's more than $1.07, I can tell you that. So we could save money while doing the right thing. Now, this is not a vessel that will be usable directly as a research vessel, but it illustrates what can be done. So it came to Miami. I met the vessel in the middle of the Atlantic by email, and I gave them sailing directions to get them to Miami. And I was a member of the Miami Yacht Club at the time, and I arranged dockage for them in Miami while they were there and helped them run logistics, go grocery shopping, clear customs, stuff that you do when you come to a foreign country. And the mayor of Miami, Manny Diaz, at the time, was very interested in solar energy, particularly photovoltaic, and they put up photovoltaic panels around City Hall and so forth. So he got very excited when this came to town. I told him about it in advance. He declared Sun 21 Day in Miami to celebrate this wondrous event of a solar-powered vessel getting to the shoreline, and with all the whereases and so forth. And so April 2nd, 2007 was Sun 21 Day in Miami. He distributed press kits to all the major news organizations, and none of them picked it up. There were people from Europe. Every country in Europe was represented. The Canadians had people here. Most South American countries had reporters here. The Miami Herald building was in walking distance, in sight of the place where it was docked, as was Channel 10 at the time. And the only way we knew it happened was BBC News was rebroadcast by WLRN in Miami, God bless them, and told us that this was actually happening. So it was a weird juxtaposition. We had the Cuban mafia that ran the yacht club trying to lick the boots of the Cuban mayor of Miami, and the Swiss people who were highly cultured decided to thank them by playing a violin duet. It was one of the most kind of surreal events I've been to in a while. So it worked. It was amazing. And they marinized the vessel. They put in waterproof hatches because they were taking this out in the ocean where you can have real waves. And they increased the strength of the cross beams because it's going to have more stresses. And so each side of the vessel has its own power system. So there's a 48-volt battery in the port hull and then the starboard hull. This gets down to the individual hulls. And so the battery contains enough power to run it day and night for 2 days. And so this vessel is like the Energizer Bunny. It just keeps going and going and going and going. You never put any fuel anywhere. The only fuel on the vessel was a little propane to run the cooking system, and that was it. So there was no liquid fuel that was used. And so it's an amazing thing. It's almost like it's relentless. And this is one of the motors. These are 90% efficient 8 kilowatt hour motors, and they run silently. You go to the engine room on this vessel and it's stone cold quiet. The only noise you hear is like a little hum of a fluorescent light in a still room. That's the noise. It's not deafening, and if you go into most of engine rooms, you have to wear special ear protection so you don't wreck your ears, and it's sweltering hot in there because the internal combustion engines are so inefficient. They just throw off masses of heat, so you're sweating down there, you're getting your ears pounded in. Go here, it's stone cold quiet, and it's cool because these motors are 90% efficient. Fossil fuel motor may be 20% efficient if it's got a turbo on it. That other 80% turns into heat, guys. That's why the engine room is so stinking hot. And so I joined Sun 21 going north. I was teaching, so I couldn't join the whole thing. And went from Sebastian up to St. Augustine, and we were motoring into a very stiff north wind, and it was just a beautiful thing, very quiet. You could actually hear what the birds are saying to each other. When the dolphins come on the bow, you can hear them blow. It's not like if you go out on the regular boat, all you hear is roar, and all you smell is smoke. And this is beautiful. We went up the Intercoastal Waterway past the first wildlife refuge designated by Theodore Roosevelt. A German immigrant was obsessed because people were attacking the pelicans that lived on this island, breaking the eggs and harassing them. And so he wrote his president and he said, we should do something about that. So Teddy Roosevelt created wildlife refuges out of thin air, made them into an executive order, and appointed the German immigrant to be the guy in charge of the wildlife refuge to protect the pelicans. So now he had an official hat and an official badge and official stuff he could chase people off with. That's the first of about 300. You could hear what the pelicans were saying to each other as we passed this island. It's beautiful. So it was quiet. I was very inspired by going with these people. So they were looking for somebody to introduce an ecological constitution to an American audience. And so I wrote a intro for that, which they published as an epilogue. And they presented this to the United Nations on May 9th, 2007. So first time I ever went to the United Nations, I actually had something that was presented to the United Nations. Kind of a neat thing. Wonderful uplifting people. The starboard hull had the crew that ran the ship logistically. They were the meat eaters. The ones in the port hull were vegans. Those were the inspirational leaders, the thought leaders, so to speak. And so I had to take 2 shopping expeditions to the grocery store and so forth. But it's home ported in Basel, Switzerland, and it might sound funny to have a port in Basel, but it's on the Rhine River, which entitles them to have a port. And so this is the safe arrival in New York City. I joined them for the last day from Staten Island, past the Statue of Liberty, and we passed this massive group of oil tankers that were anchored in the roadstead in the outer harbor, waiting for their turn to unload oil. And so this vessel had come across the ocean without using a drop of oil. And so the press boat made a big deal out of that. The Swiss know how to organize things. So they had the mayor of New York greet the vessel. They had the same quartet that was part of the Titanic serenade us, and a wonderful reception on Wall Street, etc. So, second boat that influenced my thinking, I've had this McGregor 36 catamaran for a long time. I've taken it to the Bahamas for a month, a dozen times. And so here we are in the Bahamas. The boat is fully loaded with a month of cruising supplies. And we're clipping along here, got it dialed in at about 20 knots. That means the sails, in order to get that speed, are producing about 200 horsepower. We don't usually think of sails in terms of horsepower, but they produce power. And if the boat you have is fast enough, they can produce a lot of power. And so, the other thing the boat in this iteration had a full trampoline that went across, that very lightweight. I divided the deck in 3 parts so that I could launch things through the pitch and roll center, which we'll see in a minute. So the key to catamaran efficiency is having a slender hull form, and you need a length to beam ratio of about 12, which is a good compromise between load carrying and efficiency. So if you made it too skinny like a rowing shell, like one of the 8-man rowing shells, then you'd have, it'd be very tippy and unusable, and you wouldn't be able to carry much weight. And so this is about the ideal length to beam ratio at the waterline. The bigger the waterline area is, the stiffer the restoring moment is. So it's a rougher riding boat if it's got a big water plane. It's a smoother riding boat if it has a smaller riding plane. So that's one of the reasons that none of my children get seasick on this boat, but they get seasick on almost every other boat they ever go on. That's called being sea kindly. It means something. It means that your children want to come back year after year because it's fun. So we've talked about the development of, we're scaling up the production of solar panels all over the world. Chinese builders are building more than anybody, but the Germans are well represented. There are a number of other, US makes a significant number of solar panels. And so every time you double the amount of solar panels being produced, you cut the price by about 15 or 20%. So anywhere in the globe, if you increase the amount of production, it's kind of like the oil thing. When the oil price goes up one place, it goes up everywhere. When it goes up, down pretty much in phase. So that's why we've gone from $74 a watt to 15 cents a watt. We've just scaled the production. I mean, the fossil fuel people have had over a century to do that. And we have not had that much time, but we're making progress. We're making up for past time. And so this is a house that I've visited repeatedly in my sustainable living courses. I've taught, ever since I met the guys on Sun 21, I've been teaching sustainable living at UM up until this semester. They were a real inspiration to me in writing the epilogue for the Ecological Constitution. It was something that really got my attention, made me think about big picture, which was of course what they were intending to do. So this house has a solar array on the top of it. These are the PV panels that make electricity. It has a significant 15 kilowatt array. Half of that would do very well on my McGregor 36 for power. And there have not only been increases in photovoltaic efficiency and reductions in cost, but there's also a lot of diversity, different designs that you can choose that have different purposes. And so you can pretty much tailor, you can get solar panels that are part of your window if you want. So, I mean, there are all kinds of options, and the more that are produced, the more the options go. And there's also been a substantial increase in lithium-ion production and options, largely due to the Chinese and increasingly due to Tesla. And then the ability to do AC to DC two-way conversion with a 90% or better efficiency is key to doing regeneration and making the most out of the power sources that you do have. Most of them produce DC power, and you need it as an AC, but when you regenerate it, it has to go back into DC if you're going to store it. So a round trip efficiency of 90+% is a big deal. So when you're running along South Dixie in your electric car, instead of stepping on the brakes for the red light ahead, you just take your foot off the accelerator, and your electric motors turn into generators, and it puts it back in your battery so you can use it over and over and over again. If you use friction brakes, it turns into heat, and you have no way to get it back. Once that has happened, you're out of luck. So there's been increases in efficiency of electrical propulsion, motor design, and regeneration design by proxy. And there have been some major improvements in propeller design. Those have been substantial. Now, propellers hadn't made much progress for a long time, and a Russian spy named Walker figured out he could make some money by selling US secrets to the boys in the Kremlin for a lot of money. And so he told them how the US makes non-cavitating propellers for nuclear submarines, which have a very neat spiral kind of design. And so that's a huge increase. And so we can thank Mr. Walker for the availability on the general market, because the word is out. So it has had a good side, as well as the national security. The guys in the Pentagon named the new Russian class of submarines the Walker class, because of the duplication. So this is another sailboat. This one is called a Concer 47E, and this picture shows it regenerating while tooling along at about 20 knots. And so this vessel is very fast. In those days, they had to use lead acid batteries because cheap lithium-ion batteries had not been perfected. And so in spite of that extra weight, it's creaming along here. I took a demo sail in Miami at the boat show, and we were making about 18 or 20 knots while regenerating at 15 to 20 amps on each side at 150 volts. That's enough power you could weld with it. So here's a boat that was designed for the tourist trade. This Concer 47 was made to carry 48 passengers from Los Angeles to Catalina Island, and with zero fossil fuel. So it had batteries, it had regeneration, it had sails, and of course you can plug it into the dock if you happen to be on either end of it. So you could recharge batteries in the case that there wasn't any wind. And so it was just an amazingly efficient vessel. And it had two widely spaced electrically controlled propellers, which provides insane control. When you're doing oceanography, setting moorings or sampling corals or what have you, you want to have very fine control of the vessel so you don't run into things you don't want to run into. And with electric control, it is the most finely tunable thing. You have these two little levers, a port and starboard lever, and you can make the vessel just stop, which is almost impossible to do with a diesel boat, which you're clutching in and out, and of course you're smelling the smoke. So this is like insanely easy to control, and you don't need fancy controllable pitch propellers, which cost a lot of money, and they're brittle. If you run to the bottom with them, it's a big paycheck to put them back together. And so it uses four large propeller blades, and so you feel like the boat is one with the water. There's so much propeller area. If you put this thing in reverse, you can stop the boat in half a boat length from a speed like 20 knots. I mean, it's a boat with brakes. Can you imagine? And so it's regenerating while you're putting on the brakes, and you might break your spinnaker or something like that when you put on the brakes that hard, but the boat will stop. And so having this independently controllable port and starboard is just absolutely beautiful. It means that you can tune the speed. You pick a set point, the speed you want to go. If you're not going that fast, the battery produces the power that makes up for that. So you accelerate to that speed. If you're going faster than that, it's regenerating and putting the power back in the battery, where you can use it over and over and over again, like your Tesla on South Dixie. And so it's an amazing thing. When you're going to windward in the boat over waves with sails up, you slow down typically going up the crest of a wave, and you speed up going on the backside of the wave. And so it's hard to keep the sails trimmed optimally. So with this speed control, you're at the fixed speed, so you're motoring up the steep side, and you're surfing down and regenerating on the backside. So it's amazing. You can switch back and forth from being a motor to a generator, once per wavelength. And so you're going over these waves, and you're keeping your sails trimmed, you're making more power out of that. So you can cancel the leeway when you're sailing to windward. Your boat tends to slip sideways a bit, So if you put a little more power in the leeward engine, that acts like a dagger board, and you can hold the bow up into the wind and you don't slip. So having a typical diesel boat has a small propeller on it so that you don't stall the boat out when you put it in gear. And that means it's inefficient because when you're using it, it's slipping all the damn time. High inefficiency. So it's, being able to keep a standard speed up is really neat. You get optimum power as you go through the waves. And imagine that you have a boat that has some solar panels on it, and you're powering the motor to go a little faster, you're pushing the sailing rig through the air faster, you're making more horsepower out of the sails. You're using sunshine as catalyst to make horsepower in your sails. It will be a lot of fun to sail a boat like this, figuring out how to optimize all of this stuff. And it just simply makes, imagine that you have sailcloth that generates PV power. So you can be generating power the sails and pushing them through the air faster with the energy from that. Holy smokes! Now, we haven't got that yet, but if you've got the right shape of hull, you can aspire to do that. So this is the boat, 79-foot catamaran, which is design number 247, which was made for the University of Miami by Locke Crowther Design. Locke Crowther, one of the great multi-hull naval architects of all times, who was centered in Australia, built hundreds of designs. You can tell by the design number here that well bracket, things from hundreds of feet long to 20 feet long, made of all kinds of materials, and he sailed over 1 million miles on his designs in the open ocean. That's a guy that knows how the boat actually works. We bought a boat from a guy who designed riverboat gambling boats. That's who designed the Walton Smith. So if it isn't performing well in the open ocean, there might be a correlation for that. So this boat was designed to replace a 67-foot long shrimp boat hull Catalyst. If you go out to the lobby here where they display the past vessels that you hadn't had, you can see a picture of the Catalyst. So this would have been a real upgrade from the Catalyst. The amazing thing, we actually had a bid to construct this boat for $560,000 in August of 1994. That did not include the cost of a sailing rig. It included the boat with all the hard points and reinforcements necessary to install all the accessories you're going to hear about in this presentation. But that was absolutely amazing price. It turned out they had an order for 6 aluminum vessels from Walt Disney World, and they had a hole in their order book the size of that boat. And they didn't want to fire their welders, their cutters, their aluminum forming people. If you've got good tradesmen in the boatyard, by God, you want to keep them. And so I told them, why don't you, in this case, instead of donating $250,000 to the medical school this year at UM, donate it to the other Rosenstiel school, give us a $250,000 discount on building that boat, and do it at cost. We'll fill your hole in your production schedule. And so this is like, wow. It should have cost about $1.2 million all up. So this is the deal. And it would not have required a mortgage. So the ship rate would have been considerably less. So we're familiar with high efficiency in EV transport on shore, minimum wind drag, minimum rolling friction, and high propulsion efficiency paired with regenerative braking and battery storage. We know how to do that very well right now. Vessels also need minimum wind resistance, but they also need minimum water resistance. And you can have propeller regeneration as an important way of generating electricity. And this can be not only when you're sailing, but you could be anchored in the current overnight and regenerating while you're eating dinner and sleeping. And we now have much cheaper lithium-ion batteries like the solar panels. These are being produced in vast quantities And so the efficiency of production is increasing every year. There's some fluctuations with material costs, but we have driven down not only the price, but the reliability of these things. Lithium-ion batteries, if they're not well cared for, can be tricky. And so we have figured out how to do that, how to take care of them so they're not as dangerous as they were in the early days. So mass production, scaling things up, that's where it's at. So the question is what kind of a hull to make? And so displacement hulls, which are the kind that we use in research vessels for the most part, lose most of their energy efficiency through wave drag. So if you have a vessel going through the water, it makes waves. So you have a bow wave coming off a V-shaped pattern, you have a V-shaped pattern coming off of the stern, and when the vessel gets to a speed where the wavelength of that wave between the crest at the bow and the crest at the stern is equal to the boat length, that's the hull speed. So in order to go faster than hull speed, you have to have enough power to drive over the wave in front of you. That's equivalent to an aircraft breaking the sound barrier. So in order to, you have to have a lot of power to get over that hump. Now the Walton Smith was designed as a planing vessel, but then was burdened with so much fuel that it can't plane. So it spends its life trying to get over the hump at the least efficient point of operation. So the energy of the waves increase with the square of their amplitude and reach a maximum at the hull speed. And the wake energy must be supplied by your propulsion, your sails, your motors, whatever you're using to make it go. And the hull speed increases with the square root of the waterline length. But most people don't know that there's a function that multiplies that depends on how slender the hulls are. Skinny hulls make less waves than fat hulls. So the function varies between 1 for wide hulls and about 3 for slender hulls, as you can see graphically in the next slide. So this is the so-called power curve, and it shows hull speed on the vertical axis, and so shows waterline length on the horizontal axis. So these are all square root curves going up, but multiply by different values of the function. And so if you plug in the numbers for number 247, we get a hull speed of about 31 miles an hour. So this would be probably the fastest vessel in the UNO's fleet. Wouldn't go 31 miles an hour all the time, but it could. And if you're trying to get students interested in studying oceanography, it is really beautiful to be on a fast boat. And it's even better if you're on a fast boat and you're surfing. I mean, holy smokes, is that fun. It took the McGregor 36 from Gun Key in the Bahamas to the sea buoy in well less than 2 hours surfing down waves. It was just an absolute hoot. Holy cow. And that's the reason why the Polynesians got into surfing, I can tell you, and it had to do with the speed of their boats. So, looking at the contrast between single hull boats and catamarans, we have a velocity of 12 knots, and sailboats have trouble sailing straight into the wind, so they tack on the starboard side or the port side. The monohull boat has a nearly circular speed. If they have enough sail area, they can go to the hull speed in pretty much any point of sail. The catamaran, which has much less drag, gets more horsepower out of the sails and less wave drag, so the striped area between the two curves shows you what the difference in efficiency is. The only place where they're equal is when you're pinching to windward. Every other point of sail, you're going faster. And that makes a difference because now you're making more horsepower out of the sails. So any carbon reduction program begins by reducing propulsion power requirements. So naval architects summarize the power requirements for a given hull design in what's called a power curve that plots vessel speed on the horizontal axis versus horsepower required to attain that speed. And so the power curve includes not only wave drag, but wetted surface friction parasitic drag, mostly from sharp edges like immersed transoms or fittings. And then some might question the use of a hull form designed for sailing operation, but these are among the most efficient and sea-kindly displacement hull forms that are available, regardless of your propulsion mechanism. So conventional diesel or diesel electric was the least expensive propulsion in '94, so the contract was bid that way. So this shows the difference in the power curve. 247 is this one down at the bottom, with the least horsepower for the most speed. The vessel that we were trying to replace, the Calamus here, had a horsepower like this and got 8.5 knots. If you move the Calamus engines over to the 247 hull, you get another 5 knots of speed. So not only do you get places quicker, but you also, you're more comfortable because the boat isn't rolling because the sails are damping that issue. And so this is the Calamus, was that 67-foot mud boat. This is the original Atlantis at Woods Hole, which was 135 feet long if my memory serves. This is the coastal zone vessel, which we had at UM called the Cape Florida. That was about 135 feet. This was a 210-foot vessel called the Gillis, James M. Gillis, given to us by the Navy. The Columbus Island, 170-footer here, is the one that was our kind of the queen of the fleet after we lost the Gillis. So we had at one time, we had the Island, the Gillis, the Coastal Zone Research Vessel, and we had a number of smaller boats. So we had a much more capable Marine Department. Now, at the top of the figure, you see the Walton Smith. So we spend a lot of money on diesel fuel. We get big cabins in the hull because there's a lot of space down there because they're so wide to store all the oil we need to push the hull form through the water. So this picture shows the real contrast. So we're faster and we're far cheaper to operate. So the background on the design was there have been large catamarans in Polynesia that were used for thousands of years by the Polynesians to settle all of the islands in the Pacific and also to make war upon each other. They had a military purpose as well. And we based our design on a proven rugged catamaran hull which had excellent seakeeping design. It was designed to carry 16.3 long tons of pearl shells and seawater, and it was 73 feet long, also designed by Lock Crowther Design, called DMB. This boat operated in Broome, Australia, which is the most primitive part of Australia. The Brown brothers that built it are retired crocodile hunters who were prevented from hunting crocodiles anymore. So they had to figure something else to do. And so they decided to grow cultured pearls. And so if you're going to grow cultured pearls, you better have oysters. So you got to go up to the tropics where the pearl oysters grow and bring them back to Broome. And so this vessel was designed for that purpose. And so we scaled it up to 79 feet overall. It had geometrically similar hulls, but it was arranged to have a large center well at the pitch and roll center of the vessel where the forces on equipment are minimum, and it had a bridge between the hulls that overlooked the center deck where the action was. The earliest steamboats in the United States were built in New York City, and they were all catamarans. And the catamarans that Fulton built had their paddle wheels between the hulls, a nice way of supporting the pilot paddle wheels without bumping into a dock with your paddle wheels. And a great idea, and so the connecting structure between the hulls was used for navigation. And so it was called the bridge, because it connected the hulls. And so even when steamboats became monohulls, they still called that place the bridge. And so this vessel actually has a bridge in the classic sense. So I did experiments with my own little toy boat, my McGregor 36, and put in a removable panel in the center of the boat. So you can see there's a trampoline on one side, and in the middle third of the deck is a plywood section that can be removed so you can get at the sweet spot on the boat. The intersection of the pitch and roll axes, well, how do you find that? I live on a canal. It was Christmas time, and I put Christmas lights on my boat to decorate the neighborhood. And the place where that pitch axis is where the Christmas light doesn't move as the boat pitches in waves coming down the canal. So that's where the turning block ended up being. And this is a classical design, a replica of Polynesian voyaging canoe of the sort that was used to settle and war in Polynesia. And this has slender hulls. They're about the magic ratio. It has weird-looking sails. These are called crab claw sails. These were called the primitive lantine by Europeans. It turns out when they were put in a wind tunnel by Marhai, who was a Polish hydrodynamicist, these were about 50% more efficient than any other kind of sail. These are the ancestor of the delta wing, discovered by Polynesians before Christ, and used by them ever since. So here are these so-called primitive people that somehow figured out how to do this extraordinary thing. So the way it works is you have a vortex that's trapped on either side of the sail, and the spinning vortex has low pressure in the center. And if you can keep that vortex attached to the sail, you get more pressure difference than you do with just potential flow. Brilliant. Somebody back in who knows where figured it out. And so this is like natural selection. The Pacific Ocean is the biggest ocean on Earth, so the guys that figured out how to make a boat that was better, those are the ones that survived the passage. The good navigators were the ones that survived the passage. And the technology that was best more frequently survived the passage. So if you do that, repeat this over 1,000 or 1,500 years, you get to a pretty neat design. It's a little foreign to Western eyes, but pretty neat. So this is DMB. So in Broome, it has a 35-foot spring tide. You know, you think Bay of Fundy comes to the tropics. So you're surrounded by mangroves. There's corals growing in the water, or it's a little deeper because it's more exposed for like 2 weeks at a time between spring tides. So it spends half of its time aground, basically. And here it is waiting for a spring tide. The boat was very popular because the divers that pick up the pearl shells like being comfortable and not seasick. Or, you know, it takes you quite a while to get up to the tropics. So here it is under sail at 12 to 15 knots across the trade winds, 1,000 miles, essentially in comfort, without rocking and rolling. The classical pearl luggers, as they're called, have a round bottom, and they roll like crazy. So not only are they slow, but they're bloody uncomfortable to be on. So the Brown brothers, this place is so primitive, they only turn the generator on for like 10 hours a day. And so if you want to call them, you have to do it when the generator is running so the receiver will receive your telephone call. I mean, and so this boat is rugged enough that it can live out in the boondocks, it can live aground. And we often run our vessels aground, whether we talk about it much or not. We work in shallow water, so it's almost inevitable. So here it is with the sails in place, 2,400 square feet of working sails carried on 3 pro-furl hydraulic furlers. So it can be rolled up and rolled out from the bridge with minimum intervention. So you don't have to have a big crew to run the sail rig. So here's a Tesla Semi. These are already being produced out west at the big battery plant. And so they have some experience with these things. They come with a range of 400 miles at 2 kilowatt hours per mile. Remember, we were talking about 10 kilowatts for a gallon. That's bloody economical, enabling a 2-year payback. So you have a savings of $200,000 a year on diesel fuel, and compared to the cheap price of electricity. And that's before the massive increases in diesel price precipitated by the invasion of Ukraine. So it's probably a year now to do the payback. The reason I show this is not because I'm suggesting we all drive around in semis, but the battery pack that was designed for that can also be used in other things like 247. Imagine being able to put that 500-mile, a battery pack big enough to push a truck through air up and down mountains at 65 miles an hour for 500 miles. That's a battery pack. And so you could run a sailboat like 247 on that battery pack and 2 of those motor generators. So here are the general specifications. Length overall of 79 feet, beam of 34 feet. Individual hulls have a beam of 6 feet 6 inches. So when you make a monohull boat, it gets more efficient when it's long and skinny, but it also rolls more. So people who have destroyers or destroyer escorts, they're very skinny boats for efficiency, but they're very rough riding boats. People don't ordinarily volunteer to do that. So by putting them together with a connecting structure, you get around the rolling problem. You can make them skinny and not rolling. So the hull speed, 31 miles an hour, displacement, 35 long tons. Long ton is 2,240 pounds. It's an archaic unit used in marine deals. So it's loaded at 50 tons, 10 tons of cargo. That's the science outfit. Total displacement is 60 long tons. This one had twin Yanmar diesels of 175 horsepower, 2 3-bladed Hundestad controllable pitch propellers. Now with electric propulsion, you wouldn't have to bother with that because there's so much torque with electric motors, and a range of 1,250 nautical miles at 12 knots. So accommodations for 16 to 20 persons, a real upgrade from what the colonists could accommodate. And one of the key things was the society that did the classification, Det Norske Veritas, out of Norway. Those people are the most advanced in the world in catamaran designs. They have tremendous software. If you pay 10% premium to have their inspection of your design before it's built, 10 times they come to the site and see what's going into the vessel, and then at the end they do the sea trials, participate in those so that they can see that did the design meet the spec. And so they close the loop on that. And then every year, the first 2 years, then 5 years, then 10 years, then 20 years inspection, and then end of life. So they see whether the materials that they put in, the welding that was done on that vessel as it was built, how did that work? Was it good? Was it not good? So they're feeding back into the quality of the product and the quality of the designs. And if you get it built by Veritas, they just happen to sell insurance at a discount. So you can get back in 4 or 5 years, you get back that extra 10% as a discount in your insurance, and a bunch of happy Norwegians, a bunch of happy people that own the boat because they've got a quality product. ABS, which does much less with catamarans, accepts the calculations of Veritas. So this is the midships cross section. It has semicircular hull form for minimum wetted surface. It has a set of scags under it. These are hollow aluminum, and they use those for cooling fins. So you circulate fresh water that cools your engine through that fin. So you're not taking salt water into your engine. You're not taking in dead buzzards or whatever else is upstream, or spilled oil if it's an oil response vessel. And so the accommodations are double bunks, one on top of the other, so it's not palatial accommodations, but you trade that for sea kindly production. So looking forward, we have a higher sole to allow room for tankage of water or diesel or whatever you're putting in tanks. The engine room has a lower floor looking aft because you want the engine to be lower down. And then you have the laboratories above the engine room and above the staterooms. And then you have an opening in the back, and you can slide a container, a cargo container like you see over Dodge Island or around the Rasmus campus. And there's the bridge, navigation spanning the hulls, an actual literal bridge. So this is a looking down view, and the vessel has these significantly large labs that are separated from the mess area, so you're not getting chemicals mixed in with the cooking, or you're not getting cooking odors mixed in with your chemistry. And so you have a dry lab on one side, a wet lab on the other, and in the middle of the whole thing you have a big gimbal set that supports a robotic manipulator that allows you to handle your equipment robotically through the middle of the vessel when the weather gets rough. A lot of people who do oceanography or technicians that support them get injured with winch and wire accidents. The number of technicians I know well got badly injured that way. So I thought, why not make deployment so that the technicians don't have to sit under the thing they're lowering into the water. Have a CTD fall on top of them because somebody wasn't paying attention to the winch. So the vessel has this sweet spot where the pitch and roll axes intersect. And then there's a vertical spar or pendulum that runs right through the middle of that. And then it has locations for spuds on the side, hard points, so that you can put vertical poles like you see on every derrick barge on Biscayne Bay that does dock repairs. They can anchor to the bottom in shallow water that way. That's very handy if we're going to do drilling from our ship. So there are hard points where you can bolt as many spuds on there, 4 of them or fewer. And so this is the view from the bridge looking down at the deployment of a CTD from an A-frame in the middle. So we didn't have the money to buy the sails. We didn't have the money to build the robotic manipulator. That was going to have to be an add-on. And so this is using the A-frame over the middle. The captain can see what the load is doing. It's moving the least. And so you don't need restraining lines typically. I found that with my McGregor experience. It was so well behaved lowering something through the pitch and roll center of the boat. It was just amazing. I would like other people to have that same experience. So this is the different kinds of things we can do. The first stage of the motion isolation system is the Crowther hull, which is very sea kindly. Second stage is this gimbal mounted vertical pendulum, which is only 1% of the total ship mass, and is located at the sweet spot, that intersection of the pitch and roll axes. And so then you have to know how we should correct that spar to make it vertical, you have a differential GPS made by Ashtec, which can measure the tilt of the vessel within 0.02 degrees on a 10-meter baseline. So we put the antennas out on the corners, and we can measure how the vessel is moving, and so we know what correction has to be made. We can measure the attitude with resolvers of the pendulum, and so we can know what the correction signal should be without having to worry about the acceleration of the platform. So they use the systems for testing aircraft. You can measure the flexure of the wings on a vessel as an aircraft as it flies through the air with this kind of a system. So we have pairs of hydraulic cylinders that apply the corrections, and then the third stage is an accelerator that's aligned with the vertical axis of the pendulum, and that one is moved up and down using a rack and pinion drive for heave compensation. The pitch and roll center is the place of minimum heave as well. So this means you could profile a set distance off the bottom if you were studying the bottom boundary layer. You could measure the stratigraphy of the bottom. So there are all kinds of things you could use on the pendulums, different kinds of sensors you could put on it. You could put radars on the top of the sensor if you were interested in the atmosphere, or other sensors for the atmosphere that don't have ship motion in them. You could put ADCPs on the bottom, or you could have side scan sonar to measure the profile of the bottom. You could put a high energy bottom penetrating acoustic source to get deep the stratigraphy in the bottom. You could put breathing air on the bottom of the spar, so if you have divers working at the bottom, they could have a compression chamber at the bottom, or a shark cage with air they can breathe to decompress, protected from the sharks if they so choose. And so you can put all kinds of accessories. So you can have a big drill bit down there. You could set anchors, screw-in anchors, for example, with a big drill system down on the bottom of it. So there are all these different accessories you can put on. So people often, you talk about research vessels as working platforms. This is a real working platform because it has all kinds of accessories that you can use. So big dry land, big wet land, plenty of space. So we made the space bigger for the labs and smaller for the accommodation. So this is a transverse profile. So it's long and it's skinny, and there's the skegs that are the cooling thing. They also protect the tankage, which is under the midships cabins. It has a bulbous bow on both bows. That reduces the wave drag on the hull because it suppresses it. You see tankers and all that have bulbous bows. There's a reason for that. And you could actually crawl down there with a hemispherical end on it, and you could look at the reefs coming. You could put a camera that pivots at that point. You could have a forescan sonar at that point. So the midships cabins are the ones for the chief scientists and the mates and the engineers and so forth. And then there's cabins up forward for the neophytes, the newbies. And then you have the engines. That's a diesel engine in this case. If we had built this boat, we would be replacing those with electric motors right now rather than rebuilding the diesel, because the hull is efficient enough to do it. There's a generator there. We would probably keep a generator, so in case we had a long windless time where there wasn't any sun, we could still propel the boat. And it has a skeg which protects the propeller from being beat up when you ground. They didn't put a skeg on the original Walton Smith, so they busted things all the time because the propellers counter-rotate, and so it tends to bend things away from the center line or toward the center line if you run aground. And it turns out we actually already have a battery charging cable at the dock because we have shore power. So it was initially designed as an oil spill response vessel. The U.S. Coast Guard had a vessel that worked in 16 feet of water, and there's a lot of Florida that's shallower than 16 feet. And so we built a 4-foot depth vessel that could do that. Again, with a keel cooler so it wouldn't be sucking up spilled oil. And then a continuous 50-foot deep aft deck plus the center deck, so you could put oil boom in there the way fire trucks store hose. So they hook up to a hydrant and they drive away to the fire, unpeeling the hose as they go. And you do the same thing with oil spill boom. So this would be a very quick way to just deploy oil spill boom in shallow water. And so this is a plan view showing two sponsons which concentrate the oil between the hulls, and this is an oil spill recovery device in the middle, so you recover the oil that way. So oil separator. And by putting these sponsons in there, it actually reduces the draft further because you've got an additional volume added to the hull. So these are the demery of vessels that demonstrate the mil-spec oil-resistant sponson material, and with a familiar backdrop. They make these things big enough you can take bulldozers down the Colorado River on them. you have a herd of cattle you want to get across the river, they've got one for that too. These are blue collar inflatables. These are the kind of things that the Navy SEALs buy, that farmers and ranchers and the National Park Service and others that need to go places that you can't get very easily tend to buy. And so different accessories you can bolt on this research platform. 4 bolt on spuds that could be used in 20 feet or less of water, a drill rig and a vibrocoring system to the center well, articulated bipod mast to deploy sensors over the bow, or to support 60-foot cores and along with a crown block over the center of pitch and roll. 2 cranes that service the center and aft decks, which can be bolted on where those spuds go. An A-frame over the center well until we got a budget to build the pendulum design. And then the silent ship operation with vibration and isolation under the generators and electric propulsion. Sail and motor sailing for improved silence, speed, and range, and power regeneration for sail electric hybrid operation. So you can put in different additional containers on the vessel for if you're not going to use the center well. And so it'd be a great dive boat to support a dozen divers with diving bell and decompression chamber, motion compensation, heavy lift capability, power hydraulic tools, compressed air, and then stairs to easily enter and leave the water in hot showers on the way in. So a boat that's designed to support a large number of divers, since we have a big diving program with the University of Miami. And it's getting bigger as we grow our master's program. So ocean science opportunities.
John, how many more slides do you have? I think we need to
maybe 4.
We need to come to an end. It's
Okay.
it's
Yeah,
an
we
hour and
are starting
15
a little
minutes now or so.
So, a small economic scientific drilling and coring ship for nearshore work in shallow water that's economically advantageous. To get climate proxy records, a bistatic ADCP for true vertical profiles of the bottom boundary layer, CDD deployment, and various things you can do with motion stabilization. And so this is a bipod mast forward and also over the center well for doing drilling and coring. So you put a big crown block up there and you can run a drill rig from it or vibrocoring. Safety and quality of life issues, scientists and technicians working with pendulum mounted sensors roll the equipment out of the lab, make the connection to the pendulum, and then withdraw to the safety of the lab while the center well hatches open hydraulically from the bridge and their gear is lowered robotically through the middle of the ship. Engine smoke and laboratory cooking fumes are discharged from the top of the mizzen mast, the top of the bridge aft, and there are water jackets that recover waste heat for hot water. And off-the-shelf solar heater could be installed. And we've already talked about separation. When the sails are deployed, seakeeping improves, fuel economy and range improve, regeneration electric power is possible, so the ship can come home without fuel if it needs to. And steaming time between stations is considerably reduced. With motor sailing, this vessel will often be faster than any other ship in the UNOLS fleet. And these are acknowledgments. The Coast Guard contributed $35K for a study of catamaran shallow water oil spill response vessel design. The Nation Foundation is gratefully acknowledged for $35K to support the robotic ship concept, and the Crowther design $249, and 30 scientists from around the country are thanked for their letters of support and encouragement to build at 247 with a center well. And Rex Meyer, my heroes, are acknowledged for being willing to donate $250,000 for a no-profit contract to make this extraordinarily low $560,000 bid for the construction without a mortgage. This vessel would have been outfitted by cross-decking Calamus scientific equipment to start with, and has all the structure and hard points to support the spuds, the pendulum, all the sailing rig and so forth. And Rowan Offshore is acknowledged for pledging nearly new sails and roller furling from the Rowan, Louisiana, the first sail-assisted jack-up drilling platform described in Taylor 1978. 9.6 ounce Dacron sail material. This is like the clipper ships use. Really heavy duty stuff. And then the Profuro people are acknowledged, and Yanmar was going to donate a diesel for if we purchased one. And then I got an anonymous pledge for 10% discount on the marine aluminum. So these are the references, and that is the story of the vessel that was almost not a complete story, because while the bid was active for 3 weeks, the Columbus Island ran into the Lou Key National Marine Sanctuary. You can imagine what that might have done to the bidding process. What does the university do when it has a casualty like that? They stop everything for months and they study it, which is longer than 3 weeks. So I got so close, I rolled the rock up the hill. It took me about a decade to do that. I served in the UNOL's advisory council. I was in charge of the Countless Replacement Committee. I did all this stuff, and I almost got it done, close enough to taste it. So anyway, that's the story. Thank you.
Okay. Yeah, thank you very much. Very long, very comprehensive presentation. Do we have questions?
So, John, now we have the Walter Smith.
Yes, we do.
What do you think the lifespan of the Walter Smith?
Well, we're supposedly going through a midlife refit right now with the rebuild of the diesel engines. So we're going to be burning diesel fuel for a long time, a lot of it.
Just did their sea trial the other day.
It had a sea trial the other day. I mean, the people who are operating are doing a great job of operating that vessel. I have no bone to pick, but efficiency matters. And if we're going to claim to be concerned about coral reefs, the sea level rise, and hurricane intensity, and you could list those, I could make you a list as long as your arm, the things we should care about. Yeah, we should be doing something to reduce the emissions of our research platform. We should set the example. So I'm very much interested in building this vessel. I'm going to be shopping it around now that I'm retired. So we'll see. I'm not one who gets dissuaded easily, as you may have gathered. I'm still working on climate change. Yes.
So in the first part of your talk, you were focusing on power mostly in terms of propulsion.
Right.
And I guess when I think about our at-sea operations, a lot of it has to do with actually holding position.
Oh, yeah.
On a traditional vessel, there's like thrusters involved. You mentioned heave compensation, of course. And then I was also just thinking about the weight of the massive amount of stainless steel cable that we are spooling out.
Sure.
So I guess what I was thinking is how much additional power, like when you think about solar power or something, proportionally how much power would have to go into things like positioning thrusters and just also accounting for the additional weight of all of that oceanographic
Well, there's 10 tons of science cargo on this. So this vessel, the way we operate Walden Smith, we load everything wherever we need on the boat pretty much and leave it there. It's very convenient, but it also means we're carrying around a lot of weight. And so this boat, it'd be more like running Ronnie's helicopter, where you don't take everything you've ever mounted on the helicopter because it wouldn't fly, it'd be too heavy. And so in this case, you would be doing more changing of equipment. But with the cranes and with the bipod mash, you have the wherewithal to do that without hiring special help. So the idea is to have something that can take care of itself for the most part. And you maybe ship a container full of stuff to the Bahamas or to Venezuela or wherever you're working.
I guess I was sort of seeing that you were showing us like small platforms where there was just this highly efficient usage of batteries in terms of the propulsion. But like when I think about oceanographic operations, it's a lot of heavy operational load kind of
Right.
on demand. And so how would, you know, presumably you need greater battery capacity because you're not actually kind of actively regenerating the batteries.
Well, you can have generators with fuel if you need to, but the amount you can do with regeneration and batteries would absolutely stun you if you tried it. You'd be amazed. And I can say that because I ran egret for 12 months over 12 years, and it was extremely efficient, and it was like a game to figure out how you could be more efficient, how you could measure the horsepower that you were generating while you're looking at it. So yeah, it wasn't meant to replace. It turned out that when we built the Walton Smith, we were trying to replace the Island, which we had to get rid of because of the insurance claims and so forth. Running into that protected reef at Blue Key was not a reputation-enhancing move on the side of the University of Miami. And so it not only made a mess out of my bidding process, we could have replaced Callis and still had the Island. So if you needed some big heavy-duty thing, you still have the Island. And of course, we could build a vessel to do everything the Island can do at a slightly larger size. So we were replacing the Calamus, not the Island. And so after they wrecked the Island, then they had to replace that. And so that catamaran ballooned up, and everybody wanted to load everything on. The first draft of it had glass windows facing forward. That's how much experience these designers had. And there was a space of about a foot between the hulls. I mean, it was just this, they had an algorithm, they had a CAD/CAM program that had their hull form on it. And they just plugged in numbers, and out came this incredibly fat thing that was incredibly brittle. I mean, take that out in the Gulf Stream, first big wave breaking over the bow would have sunk the thing. And they took that seriously. So that was my last interaction with the Marine Committee at that stage. I did a thorough critique predicting the demise of that vessel if they took it out in the Gulf Stream, and they didn't build that one. But they did put it in portholes, and they made some concessions. But they didn't build an efficient hull.
Okay, we have this room for 2 more minutes.
Okay.
And we have a little water damage here. At least one of your water cups started to leak.
Oh.
Are there any questions from the Zoom audience? Maybe not. So I say thank you for this nice presentation.
Well, thank you.
And this will be on YouTube again.
Thank
One of
you.
the longest ones probably we have on the channel, and maybe again one of the most popular ones.
We'll see.
Thank you all for coming. The next seminar will be on Friday. We have 2 student seminars in the auditorium, again with a lot of bagels and all kinds of things. And then next Wednesday, I guess this guy will give a presentation or not. I haven't heard anything from him anymore. So watch the emails if he will be giving a presentation or not.
Okay.
Good night.
Thank you guys for coming.
Dr. Van Leer.